The topic of today's video is about the substitution rule for integration, and this one is similar to the chain rule that we use for derivatives but for integrals. Okay, so let's review a little bit of the chain rule before going into this new rule for integration. So when getting derivatives, the chain rule was used to get derivatives of composite function. Remember what a composite function was? We had regular functions that look like this. The meaning of regular function and not as opposed to a composite function is that the variable x is kind of on its own. You don't see anything else on the structure of the function. You see powers over there, or the x as an argument of the function. It's on its own. And a composite function looks something like this. What's the difference? Well, that you have a regular function inside another regular function. In this case, the green thing can be understood as being just x to the 3. So you have a regular function, this one over here, inside what would be your regular x to the 3. And that's the concept of composite function. You have a function within a function. Here's another example. This one is a regular function. This one is a composite function. This one is regular because the sign always goes with its argument, but the argument is simply x here, and the argument in the other one is something more complicated than that. It's a regular function within the place of the argument alone. So now for the integrals. When you see an integral with an integral of a regular function, you see something like this. And for this ones, you know how to integrate because you know the rules. You know, we have I don't remember, like 5 or 6 rules for getting the integrals of elementary functions. If you have something like this, you also know how to integrate power functions, and you just do it. So the question is, what happens with integrals that feature non-regular functions, like this one? Can you integrate this one? Well, this is a tricky question because the answer is yes, but not with the substitution rule that you're about to learn. I'm going to change a little bit this function. This one can be integrated with substitution, and you'll notice what do you need for that to happen. So let's integrate this function, and this is a non-regular function because this one is a composite function, and you have 2 functions actually inside the integral, so there is no rule for integrating this, and it will be a mistake to just give the answer as the integral of this bit, the integral of this bit, inside the integral of cosine or something like that. That's a common mistake. So how do we integrate this function? This one is suitable for substitution, and I think it's best explained if I do this, if I integrate this function. So pay attention. The first rule, the first thing to notice will be identify a composite function. Do you have a composite function in this integral? This integral is made up of these 2 functions. This one over here, and the one framed in purple is the only one that's a composite function. So this is your composite function now. 2. Identify the innermost element in such function. So this is your function, and if it's a composite function, it means that you have a function within that function. What is the innermost part of this composite function? Well, that's easy for this one. It's this. And then you have to ask yourself, are the outer elements of the integral in the differential of that piece? What do I mean by that? I need the differential. Let me explain what this question means by actually solving it. So to avoid confusion, I'm going to relabel this. Remember that this is the innermost element of the composite function. I'm going to call it u. So u is going to be x to the 4 plus 2. Now, if you recall the definition of a differential is basically the derivative multiplied by the differential of the variable. So the differential of u is going to be just the derivative of this times the differential of the variable x. In this case, it's just simply 4x to the 3 times the x. So that's the differential of the u. Now, are the outer elements of the integral in the differential of that piece? By outer elements, I mean whatever is outside the composite function. In this case, whatever is outside the purple box. These are the elements that are outside the purple box. Do you see them on the differential? Yes, of course, we see them here. So the answer to this question is yes. All my elements that are not in my composite function are in the differential of the u, of the variable that I just called u. Now I can make a little trick. I can just leave the elements that appear in the integral on one side of the equation for the differential. This is what I mean. The 4 that it's not there, I can move it to the other side. And now I have this. This is what remains in my integral. And it's also here in my differential, right? So the trick here is to simply get rid of them and substitute them by the expression of the differential. Now, as it stands, this is a badly written, a badly defined integral because it's mixing variables. It's mixing the u with the x. But recall that we had already said that this one was in fact what we called u. So we can apply the same trick, get rid of it, and substitute it by the u. And this is it. This integral now looks better, and it's not ill-defined. You have only u's in here. This step can be summarized as this. If the answer to number 3, if you can find the outer elements of the integral there, and also on the differential of the new variable, you replace them, you substitute them, which is what we did. If you notice, this is a new integral, only has u as the variable, so it's well defined. And there's something else about this integral. It's no longer a non-regular function. It is a regular function. You know how to integrate these kind of integrals. So do it. Solve this. The integral of this is simply sine. The 1/4 here just passes directly to the answer. And this is it. Basically, this is the end of the problem. Now, remember that the problem was originally stated in x, and you have to answer in terms of x as well. This answer is given in terms of u. So recall the definition of u and return to the original variable x. Instead of this one, we have to write this. And that's it. This is the original problem, and this is the solution. And what we did is try to identify a composite function. Identify the innermost element, which is this. Call it u, get the differential, and if the elements of the differential were the remaining ones of the integral, then we could use substitution both on u and the u to solve the integral. Okay? Basically, the substitution rule formally it's stated as this, and you're required to have a composite function like this, some function, inside another one, with very specific requirement that the differential of the innermost function is outside of the original integral. If that happens, you can always substitute it for another variable called u and its differential du to form a new regular function that can be readily integrated. And this is substitution rule. Try to practice it here. How would you solve this one? Remember that you have to first ask yourself, is there a composite function over there? Yeah, I can see that this is a composite function. The innermost part is this one, so I will call this one u. The differential is this. Second, are the remaining portions of the integral this and this in my differential? Yes, here they are. So leave them alone. Everything else, move it to the other side on the differential. So something like this. And now make the substitutions. Instead of this, put u. Instead of this, put the differential of u divided by 8. So you will get something like this. A little bit of rearranging. A little bit of rearranging here. And now this function can be readily integrated. So integrate it. So far we have this. Simplified and problem almost solved. The full solution for this, return to the axis. And this is it. So origin problem and its solution. Easy.